Hey everybody, I wanted to give you guys a little bit more detail regarding the mechanism of the oxymercuration, demercuration of an alkyne, in particular bringing you up to speed on that acid-catalyzed tautomerization. As we talked about in lecture, what we're going to see happening in this oxymercuration, demercuration is that our more substituted carbon of our alkyne is going to become the ketone. It's going to get a carbon-oxygen double bond to it, and this is going to be consistent with that idea of oxymercuration, demercuration of alkenes put a carbon-oxygen single bond on the more substituted carbon. And then this less substituted carbon is going to be the one that's going to pick up the hydrogens and is going to give us the CH3. And since we're doing this on a terminal alkyne, no matter what, we're going to wind up making what we call a methyl ketone, because the ketone has a methyl group on one side. This is a methyl ketone. And so if we think about this reaction more generically, we could do this reaction with any, with any terminal alkyne, and under the same reaction conditions, we would always be making a methyl ketone, because that less substituted carbon is the one that winds up getting two more hydrogens. So let's talk about how this works. The first step of the mechanism is going to be similar to what we saw with alkenes. The idea that the pi electrons of the alkyne are going to be attracted to the electrophilic 2+ cation of the mercury. And so we're going to see the pi electron reacting with the mercury, generating a intermediate mercuronium ion, Now, we can think about the mercuronium ion either as being the full mercuronium ion, or if we want to, we can think about a resonance structure of it, where we're going to generate the more stable carbocation, which will be the more substituted carbocation. And this resonance structure is actually the one that Klein takes on in its mechanism. So we've got our mercuronium. Sorry about that. The water coming from the sulfuric acid in water, that's the conditions of this reaction, is going to attack that carbocation. Forming this protonated intermediate. Proton transfer. Is going to generate the mercury enol. And then under the acidic reaction conditions, we're going to do a redox reaction to get rid of the mercury. This step begins with a proton transfer. Which puts a second hydrogen onto that less substituted carbon. which leaves this carbon positively charged. Let's go ahead and walk through this mechanism. Let's go ahead and walk through this mechanism. Just to kind of help keep things visible and clear, I'm going to go ahead and draw the alkyne in black. If I could get everything to stay where it's supposed to be. Let's go ahead and walk through this mechanism to help you see what's going on. I'm going to go ahead and draw the alkyne starting material itself in black. And I'm going to draw the reaction components as they're doing their thing. Let's go ahead and draw this mechanism. We'll go ahead and use our reaction components in black. And I'm just going to use the reagent components, the mercury, in red. The mercury sulfate is going to dissolve, forming a mercury 2+ cation. The nucleophilic alkyne is going to attack the mercury, giving us this kind of strange vinyl carbocation, with the mercury going to the less substituted end of the carbon-carbon double bond and leaving a carbocation right here. And of course we can draw a resonance structure of this that really shows us that cyclic mercuronium ion. In this particular example, we don't tend to do that because we want to really be able to see this regiochemistry. So I'm going to redraw this resonance structure A right here. Keeping in mind that we have a positive charge right here, an equivalent of water is going to add. And this is that water that's adding to the more substituted carbon. This oxygen is going to be the oxygen of our carbonyl. Okay. Next step, we're going to go ahead and do a proton transfer with some water, again, that's in the reaction mixture. And so now you can see we've set up almost this Markovnikov addition already of the oxygen to the more substituted carbon. Continuing with the mechanism. Let's draw a resonance structure. Continuing with this mechanism, continuing with other mechanism, we've got a lot of H3O plus present because we did add sulfuric acid. We're going to proton transfer. And that proton is going to add to give us the most stable carbocation. And for this example, the most stable carbocation going to be this one. Because we're going to be able to stabilize this carbocation by resonance with the alkox, with that the lone pairs on that oxygen. So we can see we're actually already looking a lot like that methyl ketone. What's going to happen in the next step is going to be a reduction step where we're going to lose mercury. The product that we're going to get from this reaction, let's go ahead and put on everything that came from these previous steps, or the other resonance form that we're thinking about here is this one. And by considering this resonance form, we can actually think about what's going to happen in the next step, which is going to be this reduction reaction, which is going to drop the mercury off of there. And this mercury all along has at this +1 charge. The mercury is going to be lost as Hg2+, and we're going to regenerate the enol. Again, this is not a mechanism I'm going to test you on. If you can understand that we're going to add to make the more stable carbocation and put that oxygen on the more substituted, you'll be in good shape. Now, this is our enol. And this is what we need to tautomerize in the next step to make the keto form, which is what we're going to think about as the product. So again, here's our enol form. In the presence of acid, and there's still acid in this solution, we're going to have something that's going to look a lot like the alkene hydration. Generating this carbocation with our new proton being added to this carbon right here, so that we can actually, and just for clarity, there's our red one and there's our blue one. And then some water's going to come along and remove that last proton and get us to our more stable keto form. How do I know my keto form is more stable? You could go through and do a calculation of your bond association energies, and you would find that the combination of the carbon-oxygen single bond and the carbon-hydrogen, the carbon-oxygen double bond and the carbon-hydrogen single bond is going to be stronger than the combination of the carbon-carbon double bond and the oxygen-hydrogen double bond. And so that is why we see a preference for this keto form. And then this keto form is the one that we're going to talk about and that we're going to use when we're doing synthesis. Thanks for watching.